So here in this video, we're going to use Newton's method to approximate all the given functions roots accurate to 3 decimal places. Use technology to find a good initial value. So I'm just telling you here, I'm going to start at x equal to 1. If you use technology, so here's the formula for Newton's method. If you use technology, you'll see that it's obviously a cubic, and we've got a root at looks like 0.754875, right? So that's just an approximation. We are not able to factor this thing, so that's the best we can do with technology. Now we're going to find this approximation by hand using Newton's method, all right? So it'd be pretty cool. So first thing I need for Newton's method, after I get my starting point, I need a derivative, okay? So typically the starting point is just given to you here. If it's not given to you, use your calculator to see, oh, look, the root's 0.75. Well, let me try 1. 1 seems close enough to get us back over there, closer to the root, right? So if I took something just a little bit bigger, it looks like that derivative intersects the x-axis at a point that looks closer to the solution. Okay, so the derivative of x cubed is 3x squared. Derivative of x squared is 2x. So this is my derivative function. I'm going to use this to help me calculate x1. So how this formula works, to get the next value, I take the previous one. So if I start at x0, the next one is x0 plus 1, which is x1. And that equals x0 minus f of x0 over f prime of x0, okay? So that's how that formula works. So I'm going to take my x1 value, or x0 value, and plug it in. So I have 1 minus, and then I plug in the x0 into this function here, and so that's where the 3 times 1 squared plus 2 times 1 comes into play down here. And then up top I'm plugging in the actual function. That's where the cube comes in, the squared, and then the minus 1. That's what's going on there. Okay, so I take those values, I plug it in, simplify, I get 1 minus a fifth, which is 4/5 or 0.8. So the new x value, x1, is equal to 0.8. So on this next iteration here, I'm going to plug in 0.8 for x1, and I'm plugging 0.8 into the function, and then the derivative. And where do we get those pieces? We get the function here, and we get the derivative there. So plug 0.8 in everywhere, and going through some arithmetic, I simplify, and I get 0.7568. That is my new x2. So I'm going to plug in 0.7568 into my equation to calculate x3. So it's just basically you're doing the same process. Function divided by derivative evaluated at the previous point. So it's a lot of calculator work, but it is definitely doable. And so you just type it in, get a new x value. So x3 is this one. Now I'm going to take that nasty thing. And do I have to keep going here? Well, yeah, because I want to get to 3 decimals, right? And so what do? We stop whenever the successive approximations do not differ in the first d decimal places after the decimal point. So we're trying to get accurate to 3 decimal places. Right now, I've got 0.7 matching up, 7.5, and I have 7.54 here. So this one would actually, let's see, that would be 3 decimals would be 7.56 here, and 3 decimals here would be 7.55. So we're not quite there yet, okay? I want it to match up to... actually, that would be 7.57, and this is 7.55. And so that doesn't quite match up yet, but I'm closer, right? I want to get to 3 decimals. So I think one more time through this is going to get it for us. So if I plug this value in for my x3s, I get this big old nasty thing. And guess what? Now we're down to the point where our actually more than just 3, it's actually 4 decimals that match up. Okay? So now that we have 4 decimals matching up, that means we can for sure get accurate to 3 decimals. And so my answer is going to be, well, I round this to 3 decimal places. That's going to get me 0.755 here, and this gives me 0.755 here. Okay, so it looks like we're okay. So that, my friends, is how you use the Newton's method to approximate your function's root to however many decimal places you want. You keep running through this iterative process. It looks like we did 1, 2, 3, 4, 5 iterations in order for us to get accurate to 3 decimal places. Okay.